Good afternoon, everybody. Thank you for coming, and welcome to this session during which I will talk about Internet of Things, machine learning, and a bit of salad. So I hope you will enjoy it. My name is Alexis. I'm Director of Research at Rtone. Rtone is a design house with expertise in Internet of Things. Our team have all the expertise to design an IoT device, from the electronic side to the embedded software, mobile application, cloud, as well as everything related to security by design, machine learning, data science, so everything. We also have some research projects, and part of the work I will show you during this talk is part of them. We also have some open positions, so if you are looking for a job, you can contact me and we can chat. But now about you. How many of you are familiar with machine learning? Oh, many people. And how many of you already use TensorFlow Lite? 3 people. And do you know what is indoor vertical forming? Do you heard about that? Yes, 3, 4, 5 people. So anyway, during this talk, I hope you will learn what is indoor vertical forming, why we want to do some machine learning and intelligence at the edge. I will try to introduce TensorFlow Lite and explain how to use it, and how to set up a Raspberry Pi to use TensorFlow Lite, how to build a very simple neural network model, train it to predict the lattice weight, then how to convert this model and put it into the Raspberry Pi, run prediction on an IoT device, and finally I will see some benchmark to discuss the performance and further work. That's mostly the research right now. So indoor vertical forming is a procedure to produce food and vegetable like lettuce in stacked layer, such as in a skyscraper or in a container in a warehouse. So it's becoming more and more popular on this day because it helps improve the yield of the production. You can try to optimize the taste of the vegetables because you have a very controlled environment. You can monitor everything you want, and you can very control totally the climate of the greenhouse. And you can put it in your flat, you can put it in city, you can save space. So that's why vertical farming is becoming more and more popular. And this is a product that we are designing with a startup in France that would like to design such kind of cabinets that you can put in your room, you can put in your kitchen to grow lettuce, and you can take it when you want, when you have some dinner. So we put many sensors into the cabinets. So we monitor the CO2, the dissolved oxygen, the electrical conductivity, the light, the redox potential, the water pH, the humidity, the temperature, everything that can affect the vegetable growth. We also implement different kinds of irrigation system that definitely affect the performance of the growth of the lettuce. The first one and the first two are what we call aeroponics. It's HPS, or high pressure aeroponics, and nebulization that create kind of fog, as you can see on the picture. And the two other ones are hydroponics. So there, the roots are totally immersed in the water, and there are two kinds of hydroponic system that are NFT and ebb and flow. So each one of these 4 irrigation systems are implemented in a shelf on the cabinet. So all the sensor and these actuators, the irrigation system, are controlled by what we call the motherboard, that is a Raspberry Pi. And on the Raspberry Pi, we also will use Tensorflow Lite to do the machine learning on the device. And we do some computer vision with cameras that are on the shelf of the cabinet. And our software is developed in Python. So here is our computer vision system. We use it to compute the leaf area of the lettuce to monitor the growth of the lettuce. Then the Raspberry Pi sends everything, all the data to the cloud. We can see on the cloud in real time the sensor values. And then on our research lab, we connect to the cloud on our laptop and we do everything related to data science and machine learning on our laptop using TensorFlow and using Jupyter Notebook. Why we want to do machine learning? To grow lettuce and to grow vegetable. But first, we can use it to detect anomaly, to be sure that our system is working as we expect. We would like to predict when the lettuce will be eaten. And we will try to make our vegetable looking better and taste better. And we would like to make it grow faster. Recently, researchers at the MIT published paper, and they're working on a project that's aimed to improve the taste of the basil. And they do some machine learning to make the basil taste better. And you can have a look at this paper if you're interested in. So now, why doing machine learning at the edge? First, we would like to make our system scalable to reduce the infrastructure and cloud cost. If we can do it in every cabinet, in every system, so why we need powerful server, many server, if every device can do it at the same times? We want our system to work in the field without internet. If you want to deploy such system outside or in place where internet connectivity is a real issue, like in Africa or in some place like in the Antarctic or in the space. Right now, in the International Space Station, there are some kind miniaturized system that are growing lettuce in the space, and there are some system equivalents that are deployed in Africa. And I think that it's not really an issue there with our system, but machine learning at the edge can be very useful for privacy. So now, a few words about TensorFlow. TensorFlow is a platform for doing machine learning. It's an open source library that has been created by Google, and the version 2.0 has been released last month in October. So with TensorFlow, you can create, train, debug, and use different machine learning model, neural network, but not only. It comes with many components, many API. I'm not an expert on every component, but you can use Keras to create a neural network. You can use TensorFlow Lite. I will show you in a few minutes. There is TensorBoard, that is a tool to debug and monitor when you are training a network. Also TensorFlow Probability, that it's used to do machine learning without neural network, with probabilistic model. So this figure summarizes well all the components of TensorFlow, and you can see that TensorFlow Lite is part of them. TensorFlow Lite mainly targets low-end device like mobile phone, so it supports iOS, Android, also Raspberry Pi, embedded Linux, and recently some teeny device like microcontroller. So basically it's Arduino, TensorFlow Lite come with two components. The first one is a converter that helps you to convert a keras model, a model that you have trained with TensorFlow, into TensorFlow Lite format. And it comes with an interpreter that basically is used to do inference on the device. So on the device, you don't need to install the full TensorFlow distribution, and you just need to install the TensorFlow Lite interpreter. So what are the differences between TensorFlow and TensorFlow Lite? So TensorFlow Lite helps you to build smaller model to reduce the size when you deploy it on your device because they are constrained in memory. You can do faster inference, and it mainly targets different platforms with different architecture. But with TensorFlow Lite, you can't do training. You can't train your model with TensorFlow Lite. When you convert your model, it's frozen. You can do retraining, and you can do transfer learning. So now we will see how to set up your laptop and set up your Raspberry Pi to use TensorFlow in one side and TensorFlow Lite in the other side. But before that, TensorFlow Lite comes with some optimizer that help you to reduce the size of your model and make it infer faster. So first kind of optimization are the pruning, so it helps you reduce the size of the graph. So you do that before the training. And there are another side that are optimizers that you can do post-training. And you have also some delegates that help you run inference in GPU, TPU, or DSP, if you have them on your device. So basically what you have to do, what are the difference and what are the different steps you have to do with TensorFlow on your laptop and with TensorFlow Lite on your device. So first, on your laptop, the classic workflow of machine learning is to import your dataset. You work on your data, you do some pre-processing, normalization, you select your feature, then you build your model with TensorFlow, you're using keras API or another API. Then you train your model, you optimize everything you want, then you export it, and you convert to TensorFlow Lite format with some optimizer. On your device, you have to load your model, you pre-process input data, that are data from your sensor, from your camera, or depending on your use case. You can also grab a model on TensorFlow Hub. There are already some models that are converted into TensorFlow Lite format if it corresponds to your use case. After pre-processing the data, you allocate the memory, you allocate the tensor for your model, and then you run inference and you read the output and you interpret the output. So now what you need to do on your laptop, so we will use Python 3 and pip. We will create a virtual environment, that's the method that is recommended. So it utilizes all your Python package. So you activate your environment, then you install TensorFlow, NumPy, Panda, Jupyter notebooks that we will use for data science. So on your laptop, it's pretty easy because all the versions of TensorFlow are released and up to date, so you can install the latest version of TensorFlow using pip. So here is a summary of the command as a reminder. So now on your Raspberry Pi, it's more difficult. You just need to install TensorFlow Lite interpreter. You can use pip and the official TensorFlow release, but it's not always up to date. So I'm not sure that right now you can use the latest version. I think it's 1.13 or 14. The other thing you can do is to cross-compile TensorFlow on your laptop for your device. It's a bit painful, and if you are not used to cross compilation, it can be difficult. The other way is to build Basel, that is the build system for TensorFlow on your Raspberry Pi or on your device, and you compile TensorFlow on your device. But it can take a lot of times. The other way that I will show you is to grab a model, to grab a community package that is built by someone available on GitHub, available thanks to these guys, so you can download it there and deploy it on your device, and you just have to install the package. So that's what I will show you. So like in your laptop, we will use Python 3 and a virtual environment. So here are the same things. We have some native library that you have to install using your package manager on your device. And after that, you just have to download the WH Python package that will help you to install TensorFlow Lite interpreter. And then you can check here in the Python console how it works. So here are the few commands that you have to type, and here is a URL to download TensorFlow Lite runtime. So now some demo, in two parts. The first part, I will run it on my laptop in a Jupyter notebook. I will create a very simple neural network model to predict the lettuce weight. And the second part will be deployed on the Raspberry Pi that you see there. And we just will deploy our model inside and run inference to predict the lettuce weight. So in the Raspberry Pi, I will show you in a Jupyter notebook from my laptop, but it's just because it's more easier to visualize. But in production, basically, you can create in the same way a Python script. So you should already have run that. So I will first import the package I need. I'm running TensorFlow. No, here it's just on the Raspberry Pi. So this one is on my laptop. So I import everything I need. Yeah, here is it's the RIN. It's my laptop. So the first thing I have to do is to import my dataset. I will use Panda with the Pickle format. First thing I have to do is to clean my data because some values are null, so I have to remove them. One of the columns of my data are categorical. It's the regression system I introduced a few minutes ago. We have 4 different regression systems, and I will use one technique that is the one hot. So I will convert the column with 1, 2, 3, 4 into 4 different columns. So you can see them. That is HPA and Web Fluids nebulization. Then I will split my dataset into a trained dataset and a test dataset. Now I can then visualize with a pair plot and Seaborn, just for visualization. Some stat about my data. Then I extract the label that are the weights I want to predict for the training process. One thing that we usually do in machine learning is to normalize our data to make our system converge faster. And then I build my model. So it's a very simple model. I will use Keras API with 2 dense layers and with 64 neurons in each, and using the ROLU activation function. So I build my model. Then some utility that I will use to visualize the training process with TensorBoard later. So here are some visualization of my model. So you can see here the two dense layers. And at the input of my model, I will put the 9 parameter of my dataset. And at the output, it's just one value that is the weight I want to predict. So I test everything. So here is just my model without training. So here I will train my model and some visualization of the training. So here is TensorBoard. So you can see here that after some epoch, the training process happens well. So I will hide it right now. Yeah. And so now I make some prediction. I think that it's about 80 prediction. And here I can see that the model is quite accurate. And on the x-axis, there are the true value, the value that I expect. And on the y-axis is the values that are predicted. So right now, I've created and trained a model on my laptop, so I will save it. So here I save it on my file system. Right now it's still a Keras model, so you can see that the size it's about 86 kilobytes. And now I will convert it to Tensorflow Lite format. There are two ways to do that. There is a Python API, and there is a Tensorflow Lite converter from the command line. So the first one use the Python API. So you can see here is a few lines of codes I need to type. Yeah. And here, after conversion, you can see that the model is only 20 kilobytes. And you can do the same thing with the Tensorflow Lite converter. And it's just a command line. So now it's a TF Lite format. It's okay if I want to use it on the Raspberry Pi, but if I want to put it in a microcontroller, I have to convert it to .h format, header file. So here are a few lines to convert a TensorFlow Lite model into to put it into a .h model in a header file. So here I create a .h model. It's not necessary to do that, but I can do quantization to reduce the size of my model. So I run it. So here you can see that the quantized model is smaller, and right now it becomes only 8 kilobytes. Okay, so now I will go to the second part of the demonstration, and I will run this notebook on the Raspberry Pi. So here I'm well on the Raspberry Pi. So the first thing that I have to do is to load my data. So here it's just a dataset, a Pickle dataset, because I don't have many sensors here. I don't have my cabinets, my vertical forming here. It's just a dataset I gathered. And then I just have to load my TensorFlow Lite model that I've deployed before. I feed it into the TensorFlow Lite interpreter. So you see here that I do not import TensorFlow package. I just use the TF Lite runtime. That's come only with the TensorFlow Lite interpreter. Yeah. Then I create the tensor. So I allocate memory for the computation, and I define the space memory. And then I iterate through the dataset to run inference. So you can see here that it takes about 47 milliseconds. So I just use this function time here to compute the computation time. It's not accurate, but it's just to give you a size of how much time it takes. And then I plot the results, and I see that it's quite similar to the previous without TensorFlow Lite. So the performance, the quantization doesn't really affect the performance and the accuracy of our model. So now some benchmark with a bigger model, because the model here it's tiny, just for a regression, but here some benchmark with the mobile nets, the mobile net model that is used to object recognition on picture, and we can see that the inference times with TensorFlow Lite is reduced up to 40%. And the model size is reduced for the same model with TensorFlow Lite up to 65%. So TensorFlow Lite has some limitation. You can't do reinforcement learning. You can't do transfer learning. Recurrent neural network and LSTM are not well supported. Currently, if you install TensorFlow nightly, the nightly build of TensorFlow, with some tricks, you can make the conversion of LSTM model working, but not with the official release right now. But it will be coming. There are many people that are working on that, and yeah. And not all the operations are yet implemented into TensorFlow Lite, so that's why some model can't be converted. And you can have some information about the compatibility of the model, the operations that are supported there. Now here we see that we run inference and do machine learning on the Raspberry Pi, but it's a powerful IoT. So right now, can we do that on microcontroller? And yes, we can. We can do inference on Cortex-M microcontrollers that are widely used in IoT. Here you can see some demos that has been presented last week in TensorFlow World conference, and you can do on microcontroller some gesture, speech recognition, artwork detection, as well as motion recognition. So TensorFlow Lite come with a C++ API. So it's very, very similar to the Python API. So the first thing you have to do is to include all the header file of TensorFlow Lite that come with TensorFlow distribution. Then you just load your model, you allocate the memory, then you feed the interpreter with your sensor data. So you put the sensor data into the memory that you have allocated, and then you invoke the TensorFlow Lite interpreter, and then you read the output. So it's quite similar to the Python API. So now about further work, we see that we can do inference on the IoT devices, but it's not training. So if you are lucky and you have a powerful IoT device, you can try to plug a Coral USB dongle that is a TPU USB key that make your device faster. There are many research papers working in the field of federated learning. Basically, it's what is used for the voice assistants, for the text-to-speech recognition, and it's kind of promising way to do inference on IoT device on the edge, because it distributes the computation into all the nodes you have in your network. So to summarize briefly what we see and what I hope you have learned today. So we see how to build, to train, optimize, and convert a model on your laptop, a very simple model. Then to deploy it and to do inference on your device. We see that some operations are not supported by TensorFlow Lite. That quantization reduce the model size, reduce the computation times, but does not affect accuracy. So we see that inference on IoT device on microcontroller is feasible. And with Tensorflow Lite, you can do regression, anomaly detection, object recognition, smart reply, text-to-speech, many use cases. Thank you for your attention. That's all for me. I hope you enjoy my talk, and if you're looking for an opportunity to work in IoT, we are hiring, so feel free to contact me. Thank you.